I got to upload. I keep forgetting to upload. Abdullah, if you're out there, well, you're not live because you're in class, but you will email me and yell at me, and I'll be very happy. Someone. It's hard to keep all these things in line. So what I'm going to do, I made a decision. I made an executive decision because, you know, the goal was to have like 15 quizzes, right? And we're not going to be, I mean, obviously we're like a few weeks behind. So I've decided that I'm going to assign another quiz, and it'll be like quiz 2 through 6. And it's mostly going to be like an assessment. So it's not going to be hard stuff. It's going to be more of like, what do you know now? It's going to be easy for you to get nearly full credit. I mean, you're going to have to do a little math, but it's mostly going to be, you'll have to wait and see. It's not going to be hard math stuff. There'll be a few math questions, but it's more or less going to be more general things that if you ponder for 10 minutes, you'll be able to answer. So it's more for credit than it is points, but there will be some points attributed to it. So it'll be, I'll give you like a week or two to do it, but it ain't going to take that long. It might take you half an hour of your life, and it's going to be 25 points. That's all. So instead of having 5 separate ones, we'll make one that has 5 questions. Is that fair? You'll get it. You'll see what I'm saying. It's not going to be very, very difficult. So I hope you don't stress about that. Let me pull up our homework so that I can answer questions for you. I need a sip of the scissor over here. My mouth is dry. So this is homework 4, I believe. Does that sound correct? And then some people wanted to talk about what 7B, someone asked, and then what 8 and 9. I think that was or maybe 6 was on there. Let's see what the chat was saying. Chat it up, man. Oh no, it's not what I wanted. 6, 7, and 9. So what was 6? Yeah, okay, so let's look at 6, although I don't want to do the same one that's right here, so let's sort of switch it up a little bit. This is an important thing. Look, these ideas about unions and intersections are very, very, very important in what we're going to be doing, and you really need to take the time to master these elementary questions about it. Now, some of you are like, elementary, what is he talking about? This is extremely difficult. Well, it's not really difficult. It's just new to you. Don't confuse difficult with new. So all we're doing is we're asking you, I mean, really problem 6 is asking you to, like, if you want to put this, I can put this in like 5-year-old terms. If I had 2 things of toys in my living room, and maybe some of these, one bin has a duplicate toy. And I said to my kid, I said, okay, what toys are in both? And she would look in and she'd say, well, here's Barbie, here's Chelsea, here's blah, 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 here's blah, 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 here's blah, blah, blah. And I would say, okay, is there any toys that are not just in one or the other, but in both? And then she would know that. And then I would say, well, what's in this box, but not in this box? And she would know that. That's what this is asking you to do. So let's look at this. And again, I'm not saying this to act like this is not difficult to learn, but really what you need to keep in mind is we're giving you symbols, we're giving you notation for something that if we don't ask you to think of it in terms of math, if we ask you to think about it as a kid playing in the living room, it's not difficult. So let's say we have one box. So let's do some examples. So let's say we have one box, and in one box we have the numbers 5, 10, 15, 20. And in the other box, we have some other numbers. In particular, we have how about we do 5, 6, 7, 8, 9, 10. So in set A and set B, you can imagine these are boxes and you know, a box of toys. And the thing to note is that in box A, you see the number 5, and you also see the number 5 in box B. And what we want to do is we want to come up with symbols that help distinguish what's in both, what's in one and or the other, and then we also want to distinguish what's in one but not in the other. That's what we're asking to do. So what you have to understand is that we create symbols to answer these questions. So what is A union B? Well, you can't answer this question if you don't know what this symbol represents. So the English for this sentence is you think of this as and or. So what is in A and or B? Well, that just means the guys that are in one or the other or in both. So that means that we have 5, 6, 7, 8, 9, and 10. And then we also have 15 and 20. Does anybody have a question about this? Now, to help illustrate this point, what's the next one? The next one is A intersect B. What does this mean? Well, this means must be in both. So what is in both? Well, there's only 2 numbers that are in both, 5 and 10. There is no other number that is in set A and in set B simultaneously. Does anybody have a question or a comment? Do not overthink this. Another way to think of A union B, this thing, the union symbol, means let's get everybody. This is everybody. This guy just means only the numbers or only the elements that are in both.
I literally learned this in high school. Like the word A, U, B, and B. Like,
Someone have a question?
I learned that in high school. So it says,
Mic off. All right, so now, well, you know, maybe we should go back and maybe we'll try to fit this all on one page so it's not so hard to follow. The next thing I want to look at is I want to look at A take away B. This means everybody in A, but not in B. Who is in A, but not in B? Is 5 in A? Yes, but it's also in B, so it doesn't count. Is 10 in A? Yes, but it's also in B, so it doesn't count. However, 15 is in A, and 20 is in A, but they're not in B. So again, this is going to be confusing the first couple times you're forced to do this, or not forced, but you try to do it. You have to take time and concentrate on what this stuff means. No one's pretending this is easy to learn. Remember, We are learning a new language, and we are using lots of symbols in place of words. Does anybody have any questions about this?
Yeah, question.
Yeah.
All right, so like, how'd you only get like when you subtracted A minus B, right? How'd you get only 15 and 20? I thought what about 6, 7, 8, and 9?
So the definition of what A minus B, what does the definition of A minus B mean? It says everything that's in A that's not in B. So you take the...
Oh, that's not in B. Okay.
Not in B, that's correct. So you another way to think about this, Josh, and all of you actually, is when you want to do A minus B, write out everything that's in A, and then go down the list and say, is it in B? Yes. Okay. No. Okay. You can check it off that way. So let's think of it that way when we go the opposite way. Maybe this will help a little bit. If I come now and I say, okay, let's look at B minus A now. So one way you can think about this is you can write out everything in B. So 5, 6, 7, 8, 9, 10. And then you can sort of, if you want, you can strike out, okay, what's in B but not in A? Well, is 5 in A? Yes, it's good. Is 6 in A? No. Is 7 in A? No. Is 8 in A? No. Is 9 in A? No. Is 10 in A? Yes. So really, B minus A, everything that's in B but not in A is actually just 5 and 10. Huh? I'm asking you. Yeah. See, now we're learning, right? So, very good. So, we make the observation. At least we're paying attention today. That's correct. So, look, notice I'm not just saying this because I'm teaching it right now. You should be doing this when you're doing it. When you say B minus A, you should say everything in B that's not in A. Think of it as B, everything in B, take away A. So when I say that out loud, you're right. I go, oh, okay, what's in B but not in A? 6, 7, 8, and 9. Those are the only numbers that are in B but not in A. Does that make sense? And just like when we did it above for A minus B, you say, okay, what's in A? Now, which guys are not in B? And the answer is 15 and 20. And here's a good way to check yourself, and this is also good for practice. Well, you know, it's never a bad thing to say things out loud. And I don't even know if maybe you guys do this already. I'll give you an example. When I write things, even for my job today or when I was a student writing, even if it's an English paper, a history paper, when I write a letter of recommendation for one of you numbskulls, right? What do? I read it out loud too. I don't just read it silently to myself. I read it out loud. Does it make sense? If I read out loud, A take away B is 15 and 20. And then I say, okay, what's in A but not in B? Is 5 in A? Yes. But is it in B? Yes. So it doesn't count. Right? Does that make sense? So, and don't forget, there's other words that some people use. Some people will say the complement. This is what's scary too. The complement of B with respect to A. So there's a lot of verbiage and there's a lot of symbols. It makes this difficult to learn. It just does. That being said, once you finally, I got to be honest, this set theory stuff is one of the things that even when you think you finally made sense of it, it's really one of those things where you're like, okay, I feel good about it. And then 20 minutes later, you try to do the same problem and you keep second guessing yourself. That's okay. Remember, no one's asking you to be an expert in October or December of 2020. We're asking you to learn some things, be proficient. Some of you hopefully will be above proficient. Some of you might not. That's learning. Just like if we went outside and we ran a race, some of you would be faster than me, some of you would be slower than me. That's just what it is. Does anybody have a question about this? Whew. All right. So the next question I believe someone asked about was what? Was it 6 and then 7b, I think someone asked? Let's think about it. What makes part B a little more difficult than part A is you have 3 sets. So it's sort of like there's one more thing to be considered. So instead of doing 7b, I'll do one that's very similar because I don't want to steal the fun from you. So instead of doing this distributive law, we can do one that's very similar. So which one was that? I just lost it. I hit the wrong button. So what did we do? Union, intersection. Okay, so now we'll do intersection union. So example 2. So here's what we want to do. We want to do this distributive law. So let's say we intersect A with B union C. We want to show that this is in fact the union of these 2 intersections. So again, when I keep saying the distributive law, I mean, what I would encourage you to think about from arithmetic and algebra is the following. You have this. You have A times B plus C, you guys know, is AB plus AC. So this is very analogous to that. That's why we call it a distributive law. I'm going to erase that, though, because I don't want you to get these letters all confused. So on homework, it was union, then intersection. Now we have intersection union. Okay, so here's the thing. There's a couple ways to do this. You can use that set builder notation if you want. That's fine. Or you can also just go directly in the following. Here's how I like to do it. I like to, this is my personal preference. Now, there's 2 ways to prove that these sets are equal. I can use logic to show that one set has the same exact description as another, or I can show each set, the left-hand side of the equation and the right-hand side of the equation, are subsets of each other. That's another way of doing it. So perhaps we can give you both proofs just for full disclosure. So let's do that. So let's call this proof 1. So the first thing I'll do is I'll show that A intersect the union of B and C. I'll show that that's a subset of the right-hand side. So how am I going to do this? Well, to do this, I'm going to let X be an element in it. Now, what can I conclude? If X is in here, what can I conclude? Well, by definition, this means that X is in A and X is in B union C. Okay, so what can we conclude from that? Well, what's the next conclusion? Well, the next conclusion is that, of course, X is in A, but what else do we know? We know X is in B or X is in C. It could be in both, but at minimum, we know it's in one or the other. Remember, in set theory, when we use the word or, it means and or. Or means it could be in one, could be in the other, or it can be in both. We call that an inclusive or if you study the English language. So that means there's two scenarios to consider. We can consider the scenario that X is in B and not in C, or vice versa. Doesn't matter, right? Or it's the scenario that X happens to be in both. So we now have, technically you could say that there's three scenarios. But two of those scenarios are the same. So what we often do is we use a phrase. We'll say without loss of generality. Because the argument is 100% the same the other way. Here's what I mean by that. So without loss of generality, assume X is in B and X is not in C. Now, I could have assumed that X was not in B and X was in C. I could have assumed that. It's the same exact thing. Now, you're going to say, what do you mean it's the same exact thing? Well, I have not said anything about A, B, and C. All I know is they're arbitrary sets. So this line above where X is in the union of B and C, it doesn't matter. If I just assume at minimum that it's in one of them, it doesn't matter which one I pretend to assume it's in. It can be in either case. And what I mean by that is the argument I'm going to give you is identical, except for some notation if I would have done it flip-flop. So the way we tell the reader that that's how we're going to proceed, so we don't have to write more than necessary, we say without loss of generality. Now you're going to say, oh my God, I'm so confused. Obviously you're so confused. You ain't never done this before, right? If I dropped you off in Moscow right now and the only language you ever spoke was English, you would be scared, you know what? Right? So here's the thing. You got to stop saying, woe is me, I'm stupid, I don't get it. And you have to remember that, yes, this is hard because you ain't never seen it before. Right? It's new. It's brand new. And most humans ain't going to make sense of this in 20 minutes. So you can't go home and pound salt and cry because you're confused. You got to go home and say, yes, O'Grady's right. This is hard. You're learning all kinds of new things. It's challenging. Now, not all of it's going to be like this. We will do a lot of math in here where it's not necessarily like this. And you'll feel back at home because it'll be normal math to you. But at some point, we have to bridge into this logical arguments. Okay, so here's what we know. If we assume X is in B and not in C, okay, great. Then we already know X is in A. So since X is in A, X is an element of A intersect B, and thus X is an element of A intersect B union A intersect C. Now, there's no other scenario to consider. We have killed every bird with one stone. Because now I could say, well, assume X is not in B, but in C. Well, then it's the same argument. Only I would replace this phrase with A intersects C. That's the only difference. And that's why I write this sentence, or excuse me, this phrase in the front. So the reader that's trained understands that, okay, he just killed two birds with one stone. And in fact, I've killed 3 birds with 1 stone, because in this scenario where X is in B and X is in C, then it's even more trivial that we're done. Does anybody have a question about this? So we just took an element in A intersect B union C, and we showed that that element, namely X, is also in the set on the right-hand side. That's what it means to be in there. That means you're now a subset. And by the way, and I hate to sort of sound like the bad guy, because I'm not getting in O'Grady's zone. I'm like getting loud and screaming. This is when Amy tells me I'm always screaming, and I'm like, I ain't screaming. I'm just raising my voice. One of those things, right? But you know, it takes a lot of experience with this stuff, and it takes a lot of exposure to it before it becomes something that you can do readily. You got to remember, you guys are just learning this, and then you have these big, thick textbooks, and you have the loud, obnoxious professors telling you how easy it is, and just practice it for a while, and it'll become second nature. I mean, I'd like you to, you know, in an ideal world, that's how it works, but we know that that's not how it works. We know that sometimes for a lot of us, it takes, you know, an awful lot of work to learn these things. You know, I would even be, you know, if I'm being fully honest with you, I would argue that the first class that I took as a math student where I learned this, I had no clue what I was doing. Just like most of you don't have a clue. Doesn't mean you're stupid. Doesn't mean I'm stupid. It doesn't mean you're a bad student. Doesn't mean I was a bad student. It just means that there's a learning curve to this. Now, some of you do get this quickly, and that's great. Good for you. You're also the kid that could do, you know, 15 chin-ups when you're in 7th grade, and good for you, right? Right? Or, you know, every one of us gets good at certain things at different paces. So we got to understand that when we're doing this. Okay, so that's one side of it. So now we have to go the other way. Now, if we want to do this problem, we have to now take the right-hand side, take an element in there, and show that it's in the set that's on the left-hand side of the equation. So here's how we're going to do that. I'm hitting the wrong button. I thought I got out of that habit where I'm hitting this mouse for this monitor, and I'm like, why isn't my screen working? All right, so here's what I'm going to do now. Now I'm going to let X be in the right-hand side. What was the right-hand side? It was A intersect B union A intersect C. What does this mean? Then we know that X is an element of A intersect B, or X is an element of A intersect C. Now, in either scenario, where is X? One thing we could say for sure, it's an A, right? We know it's an A, so that's good news. So what does this mean? This means that X is in A. Now let's be very careful. Now, remember what the left-hand side of the equation was. The left-hand side of the equation was A intersect B union C. And again, it's hard when you say these things out loud. You have to remember that with three sets in play, we have to remember these grouping symbols matter. They tell us the order in which we operate. Okay, so what can we make from this line? One thing that we can definitely infer from this line is that X is an A. But what else can I infer? Well, yeah, it has to be in B or C. So what we can say for sure is that it's in either B or C. But what this means is, thus, X is in A and X is an element of B union C, which of course implies that X is an element of A intersect B union C. And furthermore, we get that A intersect B union A intersect C must be a subset of A intersect B union C. This seems very awful, like very convoluted, but if you take your time and slowly go through this and reason slowly, you will see that there's no gaps in our logic. Our reasoning is quite perfect. Now, perhaps we can write it and it flows a little better. Maybe this isn't as pretty as a way of writing it up, but it is in fact logically sound. Does anybody have a comment about this? So what we did is we showed two sets were equal, and we showed that they're equal by taking one set and showing it was a subset of the other, and then reversing that. That is one way of doing it. Now, of course, we can also prove this in a slightly different way, and we'll do that next. If you want to use things a little differently. When I say prove it in a different way, the logic is very much the same. It's just our presentation. All right. Let's do the secondary. Let's do, not secondary, but let's do a second proof. And again, please feel free to interrupt if you have a question. Do not feel afraid to ask. This stuff is it's very confusing. So here's proof 2. I'm just going to reason it and present it slightly different. So we start with our original set. We say, okay, here's the set A, intersect B union C. So what is this set by definition? Let's be real careful. This is the set of all X such that X is in A and X is an element of B union C. That's what it means by definition. So if we rewrite this, this is X being an element of A, and let's put parentheses here to be very clear. This is X in B or X in C. Okay, now we have this statement. We have P and Q or R. So if we go back to our propositions, and we had distributive laws for that. So the distributive law in this particular sense, what is the same thing is that this guy is, okay, so how do we distribute and over the or? How do we distribute and? This is an and. We want to distribute it over the or. We talked about this back when we did propositions, which seems like an eternity ago. And so what do we have? Well, this just means X in A and X is in B. We have this creature, or X is in A and X is in C. And there's lots of grouping parentheses here. This is very unwieldy, or I mean, whatever you want to say. What's the correct word? It's scary. But this first group of parentheses just means X is in A intersect B. And these next two say X is in the intersect of A or C. And of course, this by definition is nothing more than A intersect B union A intersect C. In my opinion, this presentation of the proof is more difficult to understand. It's a lot more symbols. It's a lot higher learning curve for most of us, particularly beginners. My personal opinion, I much prefer the first proof we gave where we kind of just said, here's what we're assuming, here's what we deduce, here's what we deduce. This is much more, in my mind, it's more sophisticated and it's not as easy to follow. But it is sound. It's not flawed. It's just presentation-wise, it's a little more symbolically insane. Right? I think we'd all maybe say that, yeah. But not everybody. Maybe some of you look at this and say it's easy. I'd like to see how your brain works. But
not easy, but like I understand that a lot more than the other one.
do you really? All right.
Only because like I have to like numbers in there and think about it.
Well, that's fine. Yeah, you could definitely do this. What's cool about this particular presentation is you see that there's so many analogies with all the propositional logic and now the set theory. It's very much the same. In many ways, it's structurally the same exact thing. Any questions about this problem? So if remember, if we're going full circle, well, this was problem 7b. One of the things that I've found teaching classes like this over the last few years, and well, for a while now, 15 years or so, students often, or you guys are usually pretty good at doing set arguments when there's two sets. But if there's three or more, it's just usually like a lot of you just give up. As I said, it's a steep learning curve. So, you don't want to get discouraged. You don't want to feel like, I can't do it. Don't get, what do they call it? There's a phrase for this. Where like people, you're sitting here saying, I'm a computer science major, or I'm an engineering major, or I'm this, and then you start feeling like you don't belong because like you feel like you're confused in class all the time. And they call it like imposter syndrome. Like you feel like you're just a phony. Everybody feels stupid because it's hard. You're not allowed to take it personal, right? You just can't say I'm not good at it or I'm an imposter. You got to say, okay, this is difficult. I'm now going to sacrifice the time to do it. Now, of course, we know that not everybody wants to sacrifice time. And that's where the line usually gets drawn. You know, it's funny, you know, not to get off topic too much, but, you know, I'm 40 now, and I'm older, so I have a little more life lessons in me. You know, in all of my group of friends, many of whom I've been friends with since I was a kid, I still hang out. My best friends come over, we watch Steeler games together, and we've been doing it for 20, 30 years for some of us. And everybody's pretty successful in life now, and whether they went to school or they went to work after high school or whatever they did, my most successful friends in all lines of work are the ones who work the hardest. They really are. I mean, that doesn't mean some people don't get breaks at some, you know, sometimes where we get lucky breaks, but my buddies who have, I mean, I guess it depends on your definition of success, but people who seem to enjoy their lives and have things that most people deem successful, those are the hardest working people. So it's not just in school, it's in life. You know, sometimes we gotta sacrifice free time for whatever reason it is. If I want to learn a trade, it might take me a long time to learn that trade. I don't just wake up one day and become a master welder, right? I don't know, maybe some people do. Just like most people don't wake up and become fluent in advanced mathematics. It just doesn't work that way. But anyhow, that's O'Grady's food for thought. Take my advice for what it is. Anyhow, that's the proof. Those are two presentations of a proof. They're very much structurally the same, but they're presented differently. And I would encourage that you know, before you really struggle with 7B, make sure you can do 7A, because 7A is not quite as difficult because there's one less thing involved. It's like when you were learning how to multiply as a kid, you'd want to multiply 2-digit numbers before you tackle 4 and 5-digit numbers. Got to build that confidence. Okay, fair enough. Let's move on now to, number 8's not difficult. You just got to look up what it means to be symmetric difference. Number 9, let's just talk about this specifically because this will be our third example. So let A sub k equal 1, 2, 3. So sometimes it's easy to get overwhelmed, but if sometimes you just don't try to make it too advanced right away, you see what's happening. So notice I'm letting k be a positive integer. One of the ways we can do that is we use the bold z with a plus sign like an exponent. That tells us just not any integers, but the positive ones. So we can write out some of these sets. What's a sub 1? So let's note, before we do anything, a sub 1 is just 1. What's a sub 2? 1 comma 2. What's a sub 3? 1 comma 2 comma 3. A sub 4, 1 comma 2 comma 3 comma 4. You know, this pattern keeps going. You know, for example, what's a sub 23? Well, that's 1, 2, 3, all the way out to 23. We keep going. What's a sub 105? Well, 1, 2, all the way out to 103, 104, 105. So what we're saying is a sub k is defined like this. And what I want to know is if I continue to take unions like of these things forever and ever and ever, what do I get? And then on the contrary, what if I took intersections of these creatures forever and ever and ever, what do I get? So here's some other things. I didn't ask you to do this in the problem, but maybe you want to do some investigations. Start thinking about how these bigger ideas work. So one thing that I noticed for sure is notice that a sub 1 is a subset of a sub 2, right? A sub 2 is a subset of a sub 3. So here's an interesting fact that you might notice. And a sub k is always a subset of a sub k plus 1.
Excuse me, Professor.
Yes.
Can we go back to that last slide real quick? Sorry.
Yeah, go ahead. Sorry about that. You got to yell. God. I like that. Excuse me, Professor. Very good, Michelle. Excuse me, Professor.
Okay, I'm good. Thank you.
Kidding. You know I'm kidding. I love teaching. It's fun. The damn problem you have as a math teacher, though, is you're trying to sell something to people that don't want to learn it. No one's here because they want to learn math. All right. So if we go, so the obvious, the thing I'm writing on the next page in an arbitrary way is that a sub 2 is smaller than a sub 3. It's a subset of it, right? A sub 3 is a subset of a sub 4, right? So if we write that out in particular, this means that we have this. A sub 1 is a subset of a sub 2, which is a subset of a sub 3, which is a subset of a sub 4, right? And so this pattern continues indefinitely. It never ends. And what's more is true as well. What is the intersection now of, say, a sub 1 and a sub 2? What is the intersection of that? Well, that's just a sub 1. What is the intersection of a sub 2 and a sub 3? Well, that's just a sub 2, because if you have a set that is a subset of another one, their intersection is just the quote-unquote smaller set. So in general, the intersection of the kth set and the guy that comes after it, the kth plus 1, is just a sub k. That's another. Notice what I'm doing here. I'm not answering any questions. I am just writing things down that I observe. I am in the toy box right now, or the sandbox. I'm little Ricky the other day just putting her damn thing in the sandbox and dumping sand everywhere. That's what I'm doing. I don't know what I'm doing right now. I'm just playing around. I'm just observing how these sets play from each other, and I'm just writing this down. I'm just sort of learning as we go. Another thing that's pretty cool to notice, what if I did the union of these things? What if I unioned a sub 1 with a sub 2? Well, now this is the bigger set, right? A sub 2. And then if I union a sub 2 with a sub 3, I go, oh, okay, this is cool. So I'm learning some patterns here. And I like patterns because, well, what the heck? We like to recognize things. Now, recognizing these patterns are going to help me answer questions like number 9 is asking. What happens if I take this union forever and ever and ever? What happens if I take the intersection over and over again? What do I get? So let's look at it this way. Let's generalize my observations here. So I made some observations on this page. Now I want to generalize them. Instead of taking two guys, what if I did a sub 1, a sub 2, and a sub 3 and compared how they sort of behaved, right? So let's keep going. So if I did a sub 1 intersection a sub 2 intersection a sub 3, we know that that guy is just a sub 1, right? And then if I kept going, if I said, okay, let's add the fourth one. Well, once again, that's just a sub 1. Because the only thing they have in common is the number 1. Now, a sub 2 and a sub 3 have something in common. I have a typo here, by the way. Let me clean this up. I'm sorry, I'm getting sloppy. There's too many things that look alike here. And so, in general, if I go a sub 1 intersect a sub 2, and I do this intersection all the way out to, say, the 100th guy, this is still just a sub 1. And then why stop at the 100th? What if I just never stopped? Well, this would still just be a sub 1, we think, right? I mean, at least that's what our intuition tells us. If we kept intersecting forever, it doesn't matter because the next guy has everybody that the previous guys have, but it has one more. So that guy doesn't count. So we can trace it all the way back to a sub 1. So what this means is, this means that the intersection of all these sets is just the number 1 or a sub 1. The set that contains the number 1. That's it. Now in these symbols, this might seem scary, but just remember what these sets are. What is this set? This is 1. And then it's intersect 1, 2. And then it's intersect 1, 2, 3. The only thing that they're all going to have in common is just the number 1. That's it. Does anybody have a comment or a question about this? This is fun. At least it is for me. You know, it is cool to think about this because I do empathize with you guys. I mean, I do remember what it was like to sit in a classroom and learning this stuff and being completely oblivious. Like, what in the heck is happening? My whole life, I was good at math. I go to college to be a math major, and then in my sophomore year, they stick me in a class, and I'm like, this ain't math. Right? That's what happened. You're like, this ain't the math I grew up with. Where's the X's and the Y's and the, you know, all that stuff? Where's the calculus? Does anybody have a question about this? Now, this really isn't a proof. This is sort of us just making an observation, but I could convert this to a proof. Because how do I convert it to a proof? I can say, let X be in this intersection. And then I can do a similar argument that I did in the previous problem to show. What I'm saying is I'm trying to use your intuition for you to believe me that this is true. But I technically didn't prove it. I sort of sketched why it's true. But to prove it, I would have to do what I do. I'd have to say, let X be an element in the left-hand side, and then show that it's also in the set on the right-hand side. But nonetheless, I didn't even ask you to do that on this problem. Did I say prove it? No, I just said determine it. So you know, in my ideas, look, this is the kind of question. There's certain questions on homework you ask, hoping that someone's going to ask about it. And in fact, almost knowing that you're going to ask because it's a learning experience. This is one of those questions where I would expect most people don't know what to do here. And then we ask, and then we talk about it. And then I am showing you how a trained eye thinks of this problem. I mean, my thing that my problem solving technique is always to, you know, think of it as a puzzle. If we're asked to do something, solve an equation, or we're asked to verify something's true, or we're asked to investigate, no matter what we're asked to do, just take what you're given and think about everything you can say about it. And then decide if any of those things that you can deduce are useful. Sometimes they are, sometimes they're not. It just depends from scenario to scenario. Anyhow, let's attack the other piece now. We did the intersection piece. Now let's think about what the right-hand side is. What about the union? So this is what I want to think now. What if I take a sub 1, union a sub 2, union a sub 3? Well, we know what this has to be. This has to be a sub 3, right? And then if you don't believe it, write it out. And then if I do the first 4, I know that this is a sub 4. So what this tells me then is if I go out to say the 100th, take 100 of them, I know that the union of this is just a sub 100. So it shouldn't shock me then if I continue this pattern indefinitely. If I never stop taking unions, what do I expect this to be? Well, remember, this is the numbers 1, 2, this guy goes all the way out to 100. If I did 1,000, it would go out to 1,000. So it makes sense to us that this union might be the positive integers, or if you'd like, the natural numbers. So a compact way of writing that is that the union over all these sets is in fact the natural numbers. This is just 1, 2, 3, goes on forever and ever and ever. We can put a little purple cloud around that because we're in heaven right now. How beautiful. Let me check the time. It is amazing. It's like, it's so funny. I literally, it must be just muscle memory. I go to my phone to check the time, and I have 2 screens in front of me that both have the time. And subconsciously, I know that, but I immediately go to my phone. It's like, it's amazing how our bodies and minds do the same thing over and over again without even thinking about it. Ooh, maybe we should study that, the mind. Ooh. How are we feeling about this? Overwhelmed? Of course. Yeah, it's okay. Scary. Some of you have me before. I curve. Grades are a silly thing. I said that to the teaching students the one semester. I don't think you're in that class, Mackenzie. Math 2000. They got so mad at me. They went and told the authorities that I said grades are stupid, which they are. They are. It's the most, grades are the most arbitrary thing. Like, it's a function. That's funny. I have to assign. We talked about functions last week. That's the function. At the end of the semester, I have to assign a letter to you that's supposed to, it's so weird because in my opinion, it should be about what you know, but really it comes down to how you performed over like 4 months, right? It's a very arbitrary science, but nonetheless, it is what it is. Does anybody have a question about this problem? I think these things we talked about today are important. I think that you should try to learn them. I mean, of course, I'm going to say everything's important, right? That's what my job is. But I think that, you know, the little victories are big. If you spend a lot of time, and if any of it's just one of these problems that you feel good about now, that's a victory, right? You know, of course, you're going to get overwhelmed. You're going to be like, oh, Grady, there's 9 problems, and they have multiple parts. And I'm like, that's okay. Feel good about some of them. You know, it's like the little victories add up eventually. You know, they do. The best sort of advice I can give you. Any questions about this? Good old sets. Like the limba. Yeah, they're the limba. Okay. Does anybody have any other questions about this homework while we're on it? Any problems that you wanted to sort of? I know we talked about the first few last week. So an interesting point to this is here, a good way to sort of think about this, I don't know, I don't want to misspeak too much. Necessarily. I think, Jared, I think you were the one, I want to say it was you, maybe I don't want to pick on you, but I think you had mentioned something about a few classes ago about like, how do we define number systems almost, right? And this is really, if you want, you could think of this as a construction. This is how you would logically construct. If you were interested in how would you logically construct the natural numbers, here you go. Although a more precise way of doing it would be to let the first number be, say, 1, and then the next one would be the previous guy plus itself. And then in that way you can, from this, all you have to do is you're essentially assuming there's this number 1 out here that has its properties, and from that you can create this system of numbers we call the natural numbers, 0 to. But of course, at a course of this level and for what we're interested in, we all agree that the counting numbers are there for us, right? We intuitively enough. So it's enough for us to say, okay, these are the natural numbers. These are the integers. We believe they're there. We believe they're rigorously defined, and we call that an axiom. Okay, fun stuff. Does anybody want to say anything? This is probably a good place for us to stop. And then we'll pick back up with the function stuff on Wednesday. But I'm happy to answer any questions or any comments. Oh, by the way, I do want to say this. I mentioned at the beginning of the class about giving you this quote-unquote quiz 2 through 6 all at once. So let me just elaborate a little more. It's going to probably be about 5 or 6 questions. And then some of them, as I said, there might be 1 or 2 mathy ones. But the rest of it is going to be some straightforward stuff about the course that you shouldn't get wrong, and so you're going to get points. You think of this as a way to accumulate points. One thing I'm going to ask you to do, and I haven't decided if it'll be through Canvas or there's going to be a link, but I want to do an anonymous survey, and I hope that you guys will take it seriously, because I'm curious as to there's certain things that students just don't want to say out loud or associate with their name about things. So anyhow, I'm hoping that you'll take this survey. I don't know, again, I might do it through Canvas, or I might just link it to, like, it's called like SurveyMonkey does it. Canvas has anonymous surveys. But I want to ask you guys a few questions and your thoughts on some things, not just about the class, but everything, and how we can better, make your lives better if there's things you don't like right now. So hopefully you'll take care of that. And I'd like to have that quiz up tonight or tomorrow, and you'll have like a week to do it. It won't be a big time commitment, I promise. It'll be maybe a half an hour of your time. All right, guys. And don't forget, technically, though, we're missing 15 minutes of class because of the Roni schedule, right? Really, classes are supposed to go from 11 to 12:30, so we're supposed to make up that missed class time, face-to-face time. So, when I give you stuff like this, you can't get too mad. But anyhow, it won't be difficult. Thank you, guys, and please believe in yourselves. How about that? That's the message of the day. Don't have imposter syndrome. Believe in yourself. Thanks, guys. Have a good one. I'll see you Wednesday, or no, I'll see Anthony in 15 minutes. The rest of you, I'll see you Wednesday. All right, guys, take care. Thanks.